Hi guys, I'm Kaylee Busby, and this is our final demo for Integrated Systems Design 2. My group and I decided to do our demo on a frequency jammer, and so our variable frequency jammer device is planned to prevent incoming and outgoing communication signals, be Bluetooth compatible, and will also be reasonably sized while costing less than $300. My teammates are Eddie, Ryan, and Nick. So first, our objectives. So we wanted to create a signal jamming device that was capable of preventing communication in the 515 to 2400 megahertz range. The signal jammer was desired to be Bluetooth compatible, and it needed to be reasonably sized and of simple design. Our device is self-contained and needs no external power sources to operate correctly, and it should cost less than $300. The motivation for this project is it was originally designed as a simple cell phone jamming device. The project then evolved into military application. So our deliverables consisted of number one, an operational circuit that is able to block frequencies in the 515 megahertz to 2.4 gigahertz range, depending on the VCO RF board used. Number two, it's Bluetooth connectivity from a mobile device to the Raspberry Pi. Number three, electronic hardware is self-contained and needs no external power sources to operate correctly. Number four, the jamming device resides in an appropriate and reasonably sized housing, which you will see in later slides. And then the total cost of the product is less than $300, like I've said prior. This is the housing. So we call ourselves the Lithium Dome. And on the left, you see the outside housing. And then on the right side, you see the inside housing. And so that is all the circuit and all the components that we have used for our final design. And this, as you can see, is our block diagram.
Hello everyone, this is Ryan Messina, and the portion of this project that I'll be talking about is the hardware design. So as you can see, there's a broad outline of all of the parts, all the passive and active components that we utilized for this lithium dome or jamming circuit. The first kind of set of stuff that we used was, or I guess the main component that we utilized was this voltage controlled RF oscillator. This was purchased off of Amazon. Originally we had decided that we were going to build from scratch, from the ground up, a signal generator, which would have utilized a lot of the components that are seen on this RF oscillator. But we couldn't get a lot of the ICs in. They were all on back order from almost all the suppliers. So we ended up having to kind of try to source the signal generation part of this circuit. But this allowed us to basically use the VCO to connect to this oscillator, or use the op amp to connect to this oscillator, and it would vary with signal starting at 515 megahertz going all the way to 1150 megahertz. So based on the voltage that it sees, that's the signal that it would generate. And it operates on a 12 volt VCC, and then the V-tune portion was the 0 to 12 volts. And the next main component that we utilized was this panel mount antenna. It's broadband. It starts from 410 megahertz and can go all the way up to 5.9 gigahertz. And then basically, as you can see, based on what frequency band you're in, it has a different set of data. So the gain, efficiency, and the voltage standing wave ratio, all of that data is right here, and it does change based on what band you're operating on. There's also an example of the radiation pattern that you'll see coming out, propagating out of this antenna. I think the one that we showed was the 617 to 960 megahertz. So it'll show your XZ, YZ, XY plane of the radiation propagation. We also utilized this operational amplifier, the DAC circuit. So the first part of the DAC would be the RC filter that we used, which is essentially, turning the square wave from square pulse that's coming out of the pi into an analog. So that digital, sign kind of into an analog sign. That's what's happening. Then the op amp is allowing us to get up to 12 volts because the pi is only capable of sending a 3.3 pulse off of its rail. So then it will get sent through sent through the op amp. That'll allow it to go from, actually allow it to go from 0.7 to 12 volts. And then there's also a Zener diode on this board, which, takes approximately 0.7 volts. So that's eating up that 0.7 volts. Since we couldn't get 0 as a sign coming from the pi, that Zener diode should, absorb all of that 0.7 volts and be able to sync us down to that 0 volt range. And there was a potentiometer that was in series with a 100 ohm resistor on the feedback loop of this op amp, which allowed us to make the gain adjustable for the op amp, which was a nice addition, as well as, and so the line out that's coming from this op amp would then get sent to the VCO, the oscillator, the VCO oscillator module that we showed in the previous slide. So it goes from the Raspberry Pi. Now you're getting your 3.3 volt line that's coming into this op amp. It is then, changing it from the digital to an analog wave through that RC filter, and then the op amp is allowing us to reach up to that 12 volt limit. And then the line coming out on this proto board would then go to the VCO. And then all the materials that we use, you can see in the table that we have here. And then also it has a buck converter that's not shown on the proto board, but the buck converter is essentially, we're using a rail on this proto board that the power is going into, and it's going straight from that rail. So it's got 18 volts coming from that rail going directly to the buck converter, which was a 40. It steps anywhere from 40, or excuse me, it steps the voltage down from what we have on the rails, 18 volts, down to 12 volts. And then obviously, and then from that, that VCO that we showed in the slide that was 2 slides ago would then go to the antenna that we had talked about as well. Here we have the 3D housing that was 100% designed in-house through SolidWorks, and these are some of the renderings. So you can see that it's just, it's a pretty simple design, but the nubs on the left picture here would slide into they're kind of difficult to see, but there's a channel on the inside of this, the bottom base. So those nubs would slide into that channel, and then you would turn it to lock it in. There's a hole in the middle of the lid, which would allow us to basically just bolt our antenna onto the top, and the antenna would be, unencumbered and have full, nothing blocking the signal at all. So it would come right out of the top. But all of this was designed on SolidWorks, like we previously said, and then it was 3D printed on the Prusa Mark III printer in the ECE lab. There's another rendering. You can kind of see what's going on with the base and the lid. And then here's the final result after it was printed. Obviously it has holes in the side that were added to give some airflow so it doesn't get too hot in there with all the components that we have going on. It doesn't get very hot, but it'll allow a little bit to dissipate. And then you can see it with without the antenna on the left, and then once the antenna was installed on the right. There we go, and I will pass the next section on. Thank you very much.
This section of the presentation will provide an overview of the software components used in this project. We utilized a Raspberry Pi as our microcontroller, which has a built-in HCI component capable of Bluetooth connection. We designed a Bluetooth server written in Python that runs on boot of the Pi. We then wrote a mobile app written in Java in Android Studio developer environment and deployed the app to an Android phone. This block diagram shows the flow of our data. The phone opens a client Bluetooth socket and connects to the Pi's server. Once connected, frequency data is transmitted from the phone to the Pi. The Pi then outputs a pulse width duty cycle corresponding to the input. This is our app's flowchart. Upon start, you are taken to the app's home screen. Next, the user can enable or disable Bluetooth depending on their configurations. Bluetooth is needed to proceed. The user can then press Start Connection to connect to the Pi. Finally, the user sends frequency data to set the frequency value of the jammer. This shows our Pi software flowchart. Upon boot, our server script is started. The server then starts a connection. Once connected, the server receives frequency data and parses that data into a percentage, 0 to 100. The percentage is output as a PWM with that duty cycle to our DAC. If connection drops at any time, then we cycle back to waiting for a new connection. Finally, here is our app screen. We have a text field to enter frequency data and a send field to send the data. The current value is stored underneath the Go button. We also have a button to enable Bluetooth capability, and we have a button to start connection with the client socket.
In this section, we will go over the theoretical methods, computational models, and experimental design that went into our JAMA project. This will include some of the equipment that we use in order to test our components, as well as the IC that we ended up using in our jammer circuit. In order to analyze the capability of the antenna, we used the SV4401A handheld network analyzer by Cheligans. The network analyzer allowed us to obtain the impedance values of our antenna, which could then be used for impedance matching. It also then produced a Smith chart that included the impedance value and an approximation of the antenna's behavior in decibels across a given range. In order to analyze our circuit live, we used the spectrum analyzer. The spectrum analyzer allowed us to observe the output of the RF frequencies around our jamming circuit. We used it to determine what frequencies we were going to jam, as well as the capabilities of our chip, and to hone in on our variability. In order to determine how much radiation is outputting from our circuit to know if the range that it has, we use the electromagnetic frequency meter GQ EMF-390. And when we were using this, it allowed us to determine that our radial area around the jammer was about 6 feet. For our operational amplifier circuit, we used the LM324N IC. This allowed us to have adjustable voltage gain, which we were able to vary based on an output from the Raspberry Pi. The LM324N is a non-inverting unity amplifier IC. In order to make sure that we did not overload some of our components that required 12 volts, we used a 24-watt DC to DC buck converter. This drew voltage from two 9-volt batteries that we had connected in parallel to form an 18-volt power rail. And this allowed us to provide a constant 12 volts to our RF chip in order to power it. Some other equipment that we used to measure different components throughout our experiments was a Fluke digital multimeter. This allowed us to evaluate the tolerances of our passive components, such as resistors and capacitors, and allowed us to check connections on some of our soldered breadboards. We had to use various data sheets throughout the process in order to evaluate different IC chips as well as antennas and sometimes resistors. And then in order to do small tests before we had a stable power supply, we used our analog discovery 2 to supply voltage values as well as an oscilloscope for some of our testing.
Okay, so here we have the data and results, and to the right is a summary of the readouts that we got and the equipment that we used to collect that data. But first up is we have the antenna data. We use the network analyzer sweeping on frequencies from 620 to 960 megahertz. We chose that range because it was designated on the data sheet of the antenna as an optimal operating range for this particular antenna. When we did that sweep, we got a decibel readout of negative 3.96 and a matching impedance of 50.7 and a capacitive reactance of negative 82.8 ohms. So the circuit behavior, when we tested it using the 800 to 1600 megahertz VCO RF board, we were able to operate from the lower end on 800 megahertz up to about 1100 megahertz. And this was due to the tuning voltage of that particular RF board. It required a voltage input of greater than the 12 volts we were able to supply. The picture to the right, it shows readout from the spectrum analyzer we used to collect the data. And it illustrates that as you change the duty cycle in communication between the board and the Bluetooth app, that the frequency output by the antenna and the circuit would change appropriately. And with using this board, we were able to propagate the signal out about 6 feet radius. Next, we use the EMF 390. To the right, it shows the readouts that we have there. The RF readings from the meter gave a value of 1.498 milliwatts per square meter when we were operating on a 30% duty cycle. And at this particular duty cycle, the EF readout was similar to that was output by a cell tower, which with 30%, we were operating around the 700 megahertz range, which is consistent for most cell phone bands. Next is we have successful Bluetooth communication. Here on the left, you can see what that looks like on the end of the back end, the Raspberry Pi, all the code that runs that. It shows that it receives the bits from the app and then changes the duty cycle accordingly. To the right, you can see an earlier version of the app operating system, and it shows you, hey, you can input a frequency value here and send it on, and it'll be communicated to the RPi and the rest of the circuit, and it'll change accordingly. The challenges and bottlenecks that we came up against were being able to adequately test the prototype, just because there's not many everyday items that operate at such high frequencies and are also able to show disruptions in their operating frequencies. That's easy to observe. The signal propagation also continued to be an issue. The RF board that we use as our VCO, it has a lower range than what we would like it to, but it had a built-in low noise amplifier, which allows for the maximum propagation that we've been able to achieve. And then the availability of materials has also proved to be a major issue.
So with our final demo, we also came up with future directions and project expansions, which consist of counter jamming measures, higher quality components, and radar and GPS detection. To conclude our final demo, we were able to stay within our budget of $300 while also providing a prototype that works out as expected. Our product is able to block a range of frequencies with a range of 6 feet radially. The frequencies blocked are capable of being user-defined through the application of the Raspberry Pi and a mobile app developed by the team. And when dealing with our final demo, antenna propagation proves to be a consistent problem faced by the team during all stages of the design process. These are a list of our references. Thank you. The following video is showing our device actually working. It is blocking a signal as you can see in the video.
Okay.
So there we go. Open up on the tool locator. We got 925 there. Okay.
Okay. Okay. I'm gonna point it. Okay.
Right up there.
Yeah, you want me to show my screen?
Yep, and confirm that he can see the tag.
You can see the tag. Found tool C.
Okay.
Tool
Okay.
C.
So now,
Over the run. Bring it back. A little lower towards you. Oh, bring it. Bring it. There you go. Right there. I don't have it. That's what you
cannot
can
see the tag.
Nope. I'm gonna say it's fluctuating up. There you go. Get my front. Oh, nope, you got found tool. Ryan, bring your eyes a little bit higher. Bring yours back. Yeah, there you go. Yeah, it went away.
There we go. That's it.
Yep, we're jamming.
Yep.
There you go.
Nice.